Welcome! In this video, we'll be tackling LeetCode problem number 1929, concatenation of array. This problem tests your ability to manipulate arrays efficiently and is a great exercise for improving your understanding of array operations. Let's dive in and explore the details together. In this problem, we are tasked with creating a new array by concatenating an existing array with itself. Specifically, you are given an integer array called nums with a length of n. The goal is to generate a new array ANS that has a length of 2n. The first n elements of this array ANS should be the same as the original array nums, and the next n elements should also be the same as nums. Essentially, ANS is just nums repeated twice, or concatenated with itself. The function you write must compute this array ANS and return it. For the input, you will be provided with an integer array nums, and for the output, you need to return the resulting concatenated array ANS. Let's look at an example to understand this better. Suppose the input array nums is 1, 2, 1. The output array ANS should then be 1, 2, 1, 1, 2, 1. Here's why: the first three elements in ANS are simply the original array nums, which is 1, 2, 1. The next three elements are also identical to nums, again 1, 2, 1. When you concatenate these two parts together, you get the final array 1, 2, 1, 1, 2, 1. Now, for another example, if nums is 1, 3, 2, 1. The output for nums equals 1, 3, 2, 1 would be 1, 3, 2, 1, 1, 3, 2, 1. In this case, the first four elements of ANS are exactly the same as the input array nums, which is 1, 3, 2, 1. The next four elements are also 1, 3, 2, 1, since we are concatenating nums with itself. When you combine these two parts, the result is 1, 3, 2, 1, 1, 3, 2, 1. There's also an edge case where nums contains only one element. For example, if nums equals 5. If the input array is nums equals 5, the output ANS would simply be 5, 5. Here, the first part of ANS is just the single element, 5, which comes directly from nums. The second part is also 5, as we repeat nums. Concatenating these two parts results in 5, 5. Now, let's discuss some constraints and edge cases. The length of nums will always be between 1 and 1000, inclusive. Each element in nums can range from -10⁻6 to 10⁻6, so it's important to ensure your solution handles negative numbers, positive numbers, and 0. The output array will always be twice the size of the input, so efficiency is key, especially for larger arrays. For instance, if nums has 1000 elements, your solution should efficiently build an array of 2000 elements while maintaining the same logical structure. To solve the problem of concatenating an array, we need to create a new array ANS that is exactly double the size of the original array nums. The first half of this new array should be identical to nums, and the second half should also mirror the same elements in nums. This problem is fairly straightforward, but the challenge lies in implementing a solution that is both efficient and easy to understand. One possible approach is the brute force method. With this approach, we start by creating an empty list called ANS. Then, we loop through the array nums twice first, to append all its elements to ANS, and then to repeat the same process for the second half. While this method is conceptually simple and gets the job done, it does involve some extra looping. In terms of complexity, the brute force approach takes n time, since we iterate through nums twice, and 2n space to accommodate the new array. However, this method doesn't take full advantage of language-specific features, which could simplify and optimize the process further. Another approach to solve this problem is by using direct concatenation through built-in language operators. Many modern programming languages, including Python, provide operations that make concatenating arrays straightforward and efficient. Instead of manually appending elements through loops, we can simply use the plus operator to concatenate nums with itself. This means the desired output array ANS can be created in just one step. In terms of complexity, this approach still operates in n time since the concatenation process is all elements in the array, and it requires 2n space for the resulting array. However, the major advantage here is that the code becomes much cleaner and more concise. Additionally, these built-in operations are often optimized at the language level, making them faster in practice. It's also worth noting that while in-place mutation is often considered in array problems, it's not applicable here since the problem explicitly requires creating a new array without modifying the original input. Given the options, the direct concatenation approach emerges as the ideal strategy for this problem. It's simple, efficient, and leverages built-in language features for better clarity and performance. The key realization here is that the solution can be as straightforward as nums plus nums. There's no need for additional processing steps or manual looping, which makes this approach both elegant and highly readable. When we compare the two methods, the brute force approach, while functional, is more verbose and prone to errors due to its reliance on manual loops. On the other hand, direct concatenation provides a cleaner and more optimized solution. Both approaches have the same space and time complexity, O(2n) for space and O(n) for time, but the built-in operator is likely faster due to internal optimizations in the language. For these reasons, the direct concatenation method is the recommended solution for this problem. In this problem, we're tasked with solving LeetCode number 1929, where the objective is to create a new array ANS that's twice the length of the given input array nums. The first half of ANS should be identical to nums, and the second half should also repeat the elements of nums. For example, if the input array is 1, 2, 1, the output array should be 1, 2, 1, 1, 2, 1. This is a simple problem conceptually, but it's important to implement the solution efficiently while accounting for edge cases, such as empty input arrays or very large arrays. Let's break this down step by step to understand how we can construct the result array accurately. To approach this problem, we can structure the solution into a series of clear steps. First, it's a good practice to perform input validation. We'll ensure that the input array nums is not empty, and if it is, we can directly return an empty array since there's nothing to concatenate. Additionally, we can check that the size of nums meets the problem constraints if any are specified. Next, we initialize the result array ANS with enough space to hold both copies of nums. This means pre-allocating an array of size 2n, where n is the length of nums. This step is important because pre-allocating memory can improve performance. After initializing the result array, the next step is to populate the first half of ANS. By iterating through the original nums from index 0 to n1, we can directly copy each element into the corresponding position in ANS. This ensures that the first half of the result array matches the input array. Once the first half of the result array is populated, we then move on to filling the second half. This involves another iteration through the input array nums, but this time, the elements are placed in the second half of ANS, starting from index n and going up to 2n1. To achieve this, we adjust the indices by an offset of n so that the elements from nums are copied into the correct positions in ANS. After both halves of the array are populated, the final step is to simply return the result array ANS. Let's now examine an example to clarify these steps in action. If the input array is 1, 2, 1, we'll follow the outline steps to construct the output array step by step. In this example, the input array is nums equals 1, 2, 1. First, we initialize the result array ANS with a size of 2n, which is 6 in this case. Initially, the array looks like this, 0, 0, 0, 0, 0, 0. Next, we populate the first half of the array. We copy the first element of nums into ANS 0, resulting in 1, 0, 0, 0, 0, 0. Then, we copy the second element into ANS 1, resulting in 1, 2, 0, 0, 0, 0, and finally copy the third element into ANS 2, giving us 1, 2, 1, 0, 0, 0. After the first half is complete, we move on to the second half. We copy the first element of nums into ANS 3, resulting in 1, 2, 1, 1, 0, 0. The second element is copied into ANS 4, giving 1, 2, 1, 1, 2, 0, and the third element is copied into ANS 5, resulting in the final array 1, 2, 1, 1, 2, 1. This step-by-step process ensures that the output array is constructed correctly. There are a few key insights to keep in mind to optimize our approach. First, it's important to avoid unnecessary memory allocations. Instead of dynamically appending elements to the result array, which can be computationally expensive in some languages, pre-allocating the array ANS ensures that space is reserved up front and improves efficiency. Another optimization technique involves using modulo operations for indexing. This allows us to avoid iterating over the input array twice. For example, when filling A and S, we can calculate the corresponding index in nums using I%n. This simplifies the logic and reduces the number of explicit loops. On the data structure side, we are working with a read-only input array nums and a fixed-size output array A and S, which makes the implementation straightforward and memory efficient. Finally, let's analyze the complexity of our solution. The time complexity is O(n), where n is the length of the input array nums. This is because we iterate through the array either once with modulo arithmetic or twice when explicitly filling the two halves of A and S. Each operation during the iteration is O(1), resulting in linear time complexity overall. For space complexity, we have O(1), additional space usage apart from the result array A and S, which is essential to the problem and cannot be avoided. This makes the solution both time and space efficient, as we're not using any extra memory beyond what's required to store the output. With this efficient approach, we've addressed the problem requirements and ensured optimal performance. The provided code defines a Python class solution that solves LeetCode problem number 1929, concatenation of array. The class contains a single method getConcatenation. This method takes a single argument, nums, which is the input list. The goal of the method is to return a new list that contains the original list nums followed by another copy of nums. To achieve this, the code uses Python's list concatenation operation, implemented as nums plus nums. The plus operator is the simplest and most efficient way to concatenate two lists in Python. Here, it appends one instance of the list nums to another instance of the same list, effectively doubling its size. The method then returns the new concatenated list as the result. This implementation is optimal in terms of both time and space complexity given the problem constraints. Its time complexity is O(n), where n is the length of the input list nums, because it processes each element of the list exactly once during the concatenation. The space complexity is also O(n), due to the creation of the new concatenated list. For example, if the input list is nums equals 1, 2, 1, the method returns 1, 2, 1, 1, 2, 1. The first half of the output corresponds to the original list, and the second half is an identical copy of it. This concise and elegant solution ensures correctness while maintaining simplicity, making it a perfect fit for the problem's requirements. This is the Java implementation of the solution for LeetCode problem number 1929, concatenation of array. The method getConcatenation takes an input array nums and returns a new array that contains two consecutive copies of nums. The logic mirrors the Python solution by first creating an array with double the size and then filling the first and second halves with the elements of the input array. Key differences include explicit type declarations and the use of for loops for array traversal, which are common in Java. The implementation avoids additional memory overhead by directly copying values into the result array. To start, let's look at the example where the input array is nums equals 1, 2, 3. Our goal here is to create a new array that is the concatenation of nums with itself. This means we want to repeat the elements of nums in the same order twice. To achieve this, we use the expression nums plus nums in Python. What this does is take all the elements of the original array nums and append them to the end of the same array. In this case, the intermediate operation looks like 1, 2, 3, plus 1, 2, 3. The result of this concatenation is 1, 2, 3, 1, 2, 3. Finally, this concatenated array is returned as the output, which in this case is 1, 2, 3, 1, 2, 3. Now, let's examine a different example where the input array is nums equals 0, minus 1, 4. Once again, the goal is to create a new array by concatenating nums with itself. Using the same approach, we apply the expression nums plus nums, which appends all the elements of nums to itself. For this input, the intermediate operation looks like 0, minus 1, 4, plus 0, minus 1, 4. The resulting array after this concatenation is 0, minus 1, 4, 0, minus 1, 4. This array is returned as the final output of the function. So, for this example, the output is 0, minus 1, 4, 0, minus 1, 4. Now consider the case where the input array is empty, nums equals. Even though there are no elements in the array, the process remains the same. The goal is still to concatenate nums with itself. Using the expression nums plus nums, Python appends all elements of nums to itself. However, since nums is empty, the intermediate operation is simply plus. The result of this concatenation is also an empty array. This empty array is then returned as the final result. From this, we can note that the plus operator in Python works seamlessly even for empty arrays, creating a new list by combining the elements of the two lists, which in this case are none. The function getConcatenation essentially repeats the input list twice by this addition, and it handles lists of any size, including empty ones, efficiently. Finally, let's analyze the performance of this solution. The time complexity of the concatenation operation is O(n), where n represents the length of the input array nums. This is because the operation involves copying each element of nums twice, once for the original array and once for the appended array. In terms of space complexity, the solution also requires O(n) space. This is because the resulting array is twice the size of the input array, which means we allocate additional space proportional to the input size. Overall, this approach is efficient for creating a concatenated version of the array and works well for a wide range of input sizes. Here, we analyze the time and space complexity of the given solution. Starting with time complexity, the code concatenates the array nums with itself using the plus operator. This operation requires iterating through each element of both arrays being combined. Since nums has a size of n, iterating through it once takes O(n) time. Because the operation involves two copies of nums, the total number of elements processed is 2n. However, in big O notation, we drop constant factors, so the overall time complexity becomes O(n). Shifting to space complexity, the input array nums already occupies O(n) space in memory. Additionally, the concatenation creates a new array to store the result, which is twice the size of the input array. This means the output array requires O(2n) space, which simplifies to O(n) when we drop the constant factor. Now let's break down the remaining aspects of space complexity. No auxiliary data structures are used in this solution beyond the space allocated for the output array. This means the auxiliary space usage is effectively O(1). Therefore, the total space complexity is dominated by the memory required for the output array, which is O(n). To compare, a brute force approach might involve manually appending elements of nums to a new list twice. For example, by using nested loops where the outer loop runs twice and the inner loop iterates through each element of nums, the brute force method would result in the same time complexity since it processes 2n elements in total. Thus, the time complexity for this approach would also be O(n). For space complexity, the brute force method also creates a new list result to store the concatenated array. This means it requires O(2n) space, which simplifies to O(n). When comparing the brute force method to the optimized solution, we see that the given solution using nums plus nums is already optimal in terms of both time and space complexity. The concatenation operation directly creates a new array with 2n elements in O(n) time, and the memory required for the output array is also O(n). Additionally, the time and space complexity for this problem are consistent across all scenarios. Whether in the best, average, or worst case, the input size n determines the complexity, which remains O(n) for both time and space. Finally, the mathematical proof for the big O complexity confirms the efficiency of the solution. The concatenation operation performs a single pass over the input array nums twice, resulting in linear time complexity, O(n). Similarly, the space required for the output array is proportional to the size of the input, leading to linear space complexity, O(n). Dropping constants such as the factor of 2, we conclude that the asymptotic complexity remains O(n) for both time and space. Thus, the provided solution is optimal and efficient, making it the best approach to solve this problem. When working on this problem, there are a few common mistakes to watch out for. First, modifying the input array directly can lead to unexpected behavior. The problem specifically asks for a new result array, so altering the original nums array might not only produce incorrect outputs but also disrupt its reuse elsewhere in your code. Another frequent error involves incorrect indexing when populating the second half of the result array ANS. Remember, the second half is intended to be a copy of nums, so each element of nums should be used directly. Miscalculations here, like using nums I plus n instead of nums I, can lead to index out-of-range errors or wrong results. Finally, some users tend to overcomplicate their solutions by using approaches like nested loops or repeatedly concatenating arrays. This adds unnecessary time complexity, while a simple O(n) solution is sufficient to solve the problem efficiently. Keeping your solution straightforward will help avoid these pitfalls. Another area where mistakes often occur is in handling edge cases. For example, some solutions may fail if nums is an empty array or contains only a single element. Ignoring these scenarios can cause runtime errors or incorrect outputs, so it's essential to test edge cases thoroughly before submitting your solution. Memory inefficiency is another issue to watch out for. Allocating extra arrays or repeatedly performing operations like nums plus nums can significantly increase memory usage, especially for larger inputs. This not only impacts performance but also deviates from optimal resource usage. To ensure your solution is robust and efficient, focus on minimizing memory overhead and accounting for all possible edge cases. When solving this problem in an interview, there are several key considerations to keep in mind. First, time complexity is critical. Since the problem is relatively straightforward, interviewers will expect an O(n) solution. Avoid overcomplicating your approach with unnecessary operations, as this can raise concerns about your ability to optimize for performance. Additionally, code readability matters. A clean, concise solution that uses a single loop is often preferred over a more convoluted approach. It's also a good idea to proactively discuss edge cases, like what happens if nums is empty or extremely large. This demonstrates your attention to detail and critical thinking. Lastly, be prepared for extension questions. For instance, an interviewer might ask how you'd handle constraints like duplicates or sorted arrays, or how you generalize the solution for other scenarios. Being ready to discuss related variations can help you stand out. Looking at related problems, there are a few worth mentioning. For example, LeetCode number 238, product of array except self, is a classic problem that also involves array manipulation, focusing on achieving O(n) time complexity while carefully managing extra space. Another is LeetCode number 26, remove duplicates from sorted array, which emphasizes efficient in-place operations, making it a good exercise in array handling. Now, considering alternative approaches, one option is direct concatenation using Python's nums plus nums. While simple, this method might allocate more memory than necessary due to intermediate operations. A single loop approach is the most efficient, as it minimizes both time and memory usage by directly copying nums into the result array. Alternatively, you could use a list comprehension, such as nums I for I in range n plus nums I for I in range n, for a more concise solution. However, this involves intermediate concatenation and may be less readable to some. Weighing these trade-offs can help you choose the best approach for the problem at hand. Great job! We've successfully solved LeetCode problem number 1929, concatenation of array. Remember, mastering array manipulation is crucial for improving your coding skills. Thanks for watching, and don't forget to like, share, and subscribe for more content. See you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!